Okay, welcome everybody. Today we start our section on multivariate polynomial homotopy continuation. 1 second to set things up. Great, so we're just going to follow our nose and try to do exactly what we did in the univariate setting, and we will get stuck at a few spots, and we'll have to have a more involved discussion on how to handle things. Okay. So what could we possibly mean when we say we want to do multivariate homotopy continuation? Well, the goal, of course, is to solve now a multivariate polynomial system. And I claim we should be a little bit stuck already. So we should feel weird about this sentence. We should say, wait a second, I'm going to be a little pedantic and be like, what do you mean about that? Okay, so what could the issues be here? Yeah.
The fundamental theorem of algebra doesn't necessarily apply
In what sense?
to multivariate. So, like on the homework, actually that'd be
Yeah, you're really on the right track.
yeah. We would get different amounts of solutions compared to the degrees of the polynomial. So
yeah, so we should be concerned about anticipating the number of solutions. This was kind of like a really useful aspect in the univariate case, that if we got a degree d polynomial, we were sure that there were d solutions counted with multiplicity. And so starting this homotopy from the total degree system, x to the d minus 1, is going to do the trick. Okay. Here, we're not really sure how many solutions there's going to be. I might have, the intersection of a degree 2 polynomial with a degree 2 variety with a degree 3 variety in 2 variables, and I may not have 6 solutions. I may not be able to anticipate this number. But it's worse than that, than not being able to anticipate a finite number. Indeed, there may not be a finite number. Right, so if I have some m polynomials in n variables, m could be 1, for example, and n could be 20, right? And I would expect some really large solution set. Okay. So we don't know what it means to solve when there's infinitely many solutions. We have an idea amongst friends. So for example, if we're in 2 variables, I'd like to maybe just draw the curve. Maybe that would kind of feel like solving. Maybe somebody would be happy if you parameterized the curve, if that was possible, or parameterized the variety if that was possible. Maybe they would consider that solving. But we don't have is a good idea of what it means to solve. So I'm going to replace solve . I'll find all isolated solutions. Okay, so for example, F1 was like y minus x squared times x. And F2 was y minus x squared times y minus 1. Okay, let's unpack this in the algebra geometry correspondence. So this is a union of 2 varieties, the parabola, and it's equal to 0. Because the product of 2 things is 0, if and only if one of those factors is 0. All right, whereas this is this union. And so if I wanted to intersect these, I would get parabola and some point. Okay, so this has infinitely many solutions, but they're not all created equal. We'll get more into what an irreducible decomposition of a variety is. For now, you can kind of see that there's two parts and just have that idea in your head. Okay, there's two parts. That's all you need to know about irreducible components right now. We'll introduce it as needed. But the thing we do need now is that this solution is isolated, whereas a solution on the parabola is not isolated. Of course, we want an actual definition of this.
So zero-dimensional components.
Depending on what you mean by component, yeah.
Irreducible components.
Yeah, all of that kind of depending on what you mean by components. So of the variety, right now, of the scheme. So you can have like embedded components and stuff, but we're not gonna chat too much about that. Yeah, isolated, let's just say a point X is isolated with respect to some set if let me make this bigger. Sorry, this is kind of point X, so you can be it's isolated respect to S if you can find a ball sufficiently small so that that's the only point in the set. That should be what isolated is, right? So ball centered at X. What are we doing? Epsilon down here and X up here. Intersect. Okay, there's no little disk. You're going to throw around a point on the parabola and only pick out that point on the parabola. You're always going to pick out this. Yeah. This ball, I should remind, so I should say, is a ball in C to the n, not R to the n. You might go, okay, wait a second, like who cares, right? How could those be any different? And so I'll just say a little fact and explain it. And then we'll move on knowing this scary fact that tells us that real algebraic geometry essentially is really hard. So every real part of a variety is the real part of a hypersurface. Hypersurfaces. So hyper means one dimension less than the ambient space. So you hear this with like hyperplanes and things like that. If I'm in some 3-dimensional space, a hyperplane is 2-dimensional. If I'm in a 7-dimensional space, a hyperplane is a 6-dimensional plane. So same with hyper being used here. So if I'm in a 12-dimensional space, an 11-dimensional variety in there is called a hypersurface. Okay. Hypersurfaces are these zero sets of single polynomials. And we should think, we should hope, we should want that these are easy. Because it's just the zero set of one polynomial. Okay. For example, factoring that polynomial would give me all the components, but we're getting to that later. So maybe I'll call this f dot. And I can tell you exactly what this is. This is f1 squared plus f2 squared plus fm squared. Fact about real numbers, if I square them, they're not negative. Fact about sums of squares, if I take sums of squares, you're only going to be 0 if every summand is 0. So asking that the sum of the squares f1 through fm is 0 is the same thing as asking that f1 is 0 and f2 is 0 and f3 is 0, which is what this was in the first place. If we're considering this over the real numbers, this is not a fact over the complex numbers. Okay. So for example, this set that I drew on the board can be described by a single polynomial. If you're drawing the real picture, it'll be completely wrong over the complex numbers. Okay, so if I take f star, or f dot to be f1 squared plus f2 squared here, I get the same real picture, but this point is no longer isolated. Because in a ball and c to the n, there are other points around it. That is the thing to just know happens. Maybe the easiest way, actually, to really get a handle on this phenomenon is just take f1 to be x and f2 to be y. Together they cut out the origin. But if you do x squared plus y squared equals 0, you get many complex numbers that satisfy that. And they can be arbitrarily close to the origin. We have a question about my aspect ratio is very small. Okay, questions about that? I know we're really getting distracted from what should be a really simple discussion, setting univariate to multivariate homotopy continuation. But it would be irresponsible of me to not mention these things. We need to know what an isolated solution is. We need to know that the real picture will fool us sometimes. Yeah. Okay. We move on. Having an idea of what an isolated solution is. I didn't tell you how to even check something's isolated or anything like that. We'll get to that. So we go back, we follow our nose. What is the next thing that we did in univariate homotopy continuation? First, we identified what the heck we want to do in the first place. Now we have a well-defined thing that we want to do. We want to find all solutions. If you're being really careful, you want to find numerical approximations of the real parts and imaginary parts of each coordinate of a solution, an isolated solution here. So what should we do next?
We have like two homotopes.
What? Say
We
again?
have two homotopes.
Two homotopies?
One which takes the real part and the other for the imaginary part, something like that.
So indeed in the univariate case, we did not split a real and complex part up.
Yeah.
And we're not going to have to here.
Okay.
The real discussion was really just to indicate what isolated means and that our real eyeballs can fool us. Yeah, Jacob.
Can we instead do like a vector homotopy?
What?
Like a homotopy over vectors of functions instead of?
Yeah, so at the beginning of the course, I mentioned that a lot of your texts that you find, if you're looking around for other texts, you're going to write polynomials like here. Okay, this is going to make notation really simplified. In fact, it's going to make notation exactly the same. Okay, so this is indeed the goal. The goal is to find some homotopy where this system, if you'd like to thought about as a vector, that's merely a notational gadget, is the target system of a homotopy. Okay, so what's next? You guys can think about it. I gotta fix my display here so I can see. Any idea? What did we do next in the univariate setting? Somebody hands you some F, they want to solve, what do you do?
You just get the basic star theorem. It's a system with G, but then you have to deal with several.
Bingo, we need a start system. Okay. With what properties? Well, amongst friends, we need something that looks like this system
And has isolated solutions.
and has isolated solutions that we can compute easily. Okay.
Yeah, I mean, this could be a very stupid idea, but we could just look at degrees of F, I don't know, F1, all those elements, and we could look at, say, maximal degrees in X1 and up to Xn, and, you know, Xi, Di minus 1, something like that.
Exactly right. So perfect. That's exactly the correct start system, and it's called the total degree start system. So Rajwal suggests let's pick up start system. We'll call it G, so we don't have to switch any of our notation. It's gonna be X1 to the degree of F1 minus 1, X2 to the degree F2 minus 1, XM to the degree FM minus 1. And the two questions we ask: one, does this have isolated solutions? Two, can we find them? One of those answers is yes, and one of those answers is no currently. So can I find all the solutions? X1 has to be any of the degree of F1 roots of unity. X2 has to be any of the degree of F2 roots of unity. Okay, so I gotta pick, and let's just call this D1, D2. Yep, okay. So I have D1 choices for the first coordinate, D2 choices for the second, all the way up to DM choices for the last. So I have the product of all these DI's choices. But then, as long as M is smaller than N, it looks like I have infinitely many choices for XM plus 1 and XM plus 2, etc. And that is why we are going to put the most restrictive setting right now. So we want this system to be squared, which means as many equations as variables. Okay, now we have finitely many choices for each coordinate of a start solution. This is called the total degree start system. Or the Bezier start system.
Just so that I'm clear, when we say degree of a multivariate polynomial, we mean the highest exponent.
Yes, great question. So, degree in the univariate case is very, very well defined. No ambiguity, even amongst your worst enemy, you'll agree on what the degree should be. In the multivariate setting, that's not the case. And in fact, if you take a computer algebra class, you study Grosvenor bases, you're going to spend a lot of time thinking about what degree means. You have monomial orders and all that stuff. For us, the thing you think of before you ever thought about any of that is the degree. So for example, x cubed plus x to the fourth plus 1 has degree 5.
Yeah.
So you're adding up the exponents of every monomial. Okay. So the first monomial has degree 4, the second monomial here has degree 1 plus 4. Sorry, first monomial has degree 3, second monomial has degree 1 plus 4 equals 5, and the third monomial in this trinomial has degree 0, because that is x to the 0 plus y to the 0 plus z to the 0. So this has degree 5. Okay. Maybe I can fill the red here. Square. The red is a little bit hard. Very good. Cool, so this is the Brysiewicz start system. And it's inspired by the following theorem called Brysiewicz theorem. Which there are several, like if you Google Brysiewicz theorem, you're gonna get several different versions. This one numbers. Any system like this as well has at most D, which is the product. Y goes from 1 to n of D prime. Isolated solutions in C to the n. They might have infinitely many solutions, but at most this many will be isolated. A random / generic one of these will have exactly that many solutions, not infinitely many, this many, and they will all be isolated. And you tell your greatest adversary this, and they go, "What do you mean by random / generic?" And you say, "I don't know yet. I will tell you when Taylor gets to the next section exactly what this means." So this part, putting quotes or thought bubble. But the first part is precise. The problem is we haven't enriched polynomial systems that look like this with their own space that we can put a measure on, that we can talk about what it means to be random or generic. Right? Random means, okay, with probability 1, if you choose something randomly with any reasonable distribution, this property will happen. Okay, but we don't have any measure on the space of polynomials that look like this yet. You can absolutely imagine what that might be, and you'll probably come up with the right answer, but we're just not there yet. Questions?
This might be a bit, I might be jumping the gun here, but can we still do the geometric in multivariate? Is that still applying?
You're not jumping the gun at all.
Okay.
You're totally right? So we're gonna need some geometric, because whatever, I mean, we haven't clicked up the homotopy yet, but as soon as we do, there's gonna be some paths. And we're gonna want them to avoid all but finitely many, or avoid finitely many t values. And we'll still be doing a homotopy over just one variable t. And so we'll have to arc through that space to avoid hitting any bad points in the intermediate steps. So yeah, we'll definitely do a geometric. Not sure if we'll get to it today, but yeah. Okay. So the Brysiewicz homotopy. So here when I write x, I mean this whole n tuple of x's. Okay. In my notes, I try to make it bold. Bold with chalk doesn't really work so nice. So I'll do my best to remember this. Okay. All right, what could it be? 1 minus t times f plus gamma t times g. Keeping in mind, this looks like 1 minus t times this. Yeah. So that's the upshot of thinking about these as vector notations. But honestly, if you think about this as just like an n-tuple notation, like that still really does make sense. And we'll save tons of board space by writing it in this first way instead of the second way. But cool, we got our homotopy. That's great. So now our picture looks like this. Really similar to the one we usually write, except now the up part is a c to the n, not just a c. We have some number of solutions. Who knows how many? But here in this c to the n, we do have d solutions, and they're all isolated.
Wouldn't we require, say, pairwise coprime for that?
Good question. So Rajwal is concerned, whoa. If I have like an x1 squared minus 1 and an x2 squared minus 1, then both of those have like a similar root. And so I'm concerned that these are the same points. And they totally would be if this was a c and not a c to the n. Let's do an example. If we had degree 2 polynomials, then our start solutions are a second root of unity, comma a second root of unity, second comma a second, second comma second, and a second comma second. There are these four, and these are four distinct points in C squared.
Ah, I see.
Yeah,
I see. Okay, yeah.
yeah, that's a really good question. So the coordinates are allowed to be the same even within or
The coordinates are
around, but they're different points.
If it were just x to the power, yeah.
This is not a number theory class. It's not all those other classes I mentioned, but like it's definitely not a number theory class. Okay, any other questions? So now we need to claim that what happens here it's like what we know. Right? That we have these smooth paths that they connect the start solutions to the target solutions. And that we have some differential equation which allows us to predict from one of the start solutions what the next solution might be. So to claim that these paths are smooth, blah, 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 we need to apply implicit function theorem again, but in a multivariate setting. So in the univariate setting, it was nice. We could just kind of talk about f prime of x, and like as long as that's not 0, then we're good to we're good to apply implicit function theorem, and we locally get this smooth path, and then we march along over and over again, and that's analytic continuation. Okay, and that like notation is really simple. Here we don't have just the derivative of some polynomial. We need to endow ourselves with some differential information corresponding to capital F. Okay, and that differential information is the Jacobian of this system. And so now we have to go into a conversation about Jacobians. I mean, think about what happens. So implicit function theorem needs differential information. Davydenko differential equation, when we compose these, smooth paths with the homotopy and we get 0 and we take the derivative of both sides, that requires us doing some differential stuff. So in order to get a differential equation, we need differential information. in order to take a Newton step, think about what Newton's method is in the univariate case. X goes to x minus f of x over f prime of x. We need something to replace the f prime of x here, right? And Euler's method also is using, well, that's using the differential equation, so we're good. But we're also going to have to take a derivative there. And so we need this multivariate notion of derivatives, which you may have seen a spattering of in your previous classes. Definitely if you take an algebraic geometry. So we have 15 minutes. Let's get to it. And remove ourselves from the square setting for a moment. And we're going to assume we have m elements in n variables. Okay. Okay, good. So if you give me any n tuple in C to the n, I can evaluate those polynomials at that point, and I'll get something in C to the m. This gives me a function from C to the n to C to the m. The best, so first of all, this function may be nonlinear. I may be squaring things, cubing things, multiplying variables together, etc. But there is a best linear approximation of this function, and that is given by Jacobian. So, Jacobian. Well, I'm going to write it as a matrix. It's a linear transformation, but it's a matrix, okay? And you're going to take partial derivatives. We don't want to get this. Okay. Xj. Okay, so this is an M. I is number of rows. This is an M by n matrix, which means it gobbles up n tuples of numbers and spits out m tuples of numbers when you multiply by them. Linear transform, right? This is the differential gadget associated to a multivariate polynomial system. So now we can, let's do examples. So what is this telling us geometrically? Okay, so it tells us geometrically things in two different scenarios. One, when the variety is the implicitly defined variety by f, so the zeros of f, it's going to tell us some information about that variety, this matrix. Another is when you're parameterizing the variety, then this Jacobian will still tell us information about that variety. So let's see how that works in both cases. Let's say the variety is just the circle, the unit circle in the complex plane, okay? So what is the Jacobian here? Well, it should be a 1/2 thing. First, we take the derivative of the only polynomial with respect to x, and then with respect to y. That's the Jacobian. By the way, this notation is going to be exceptionally useful later. So D, big D, sub the variables you care about of the system. This will allow us to kind of split up the variables we care about, which will be really nice in the homotopy situation where we have x's and t's. All right, so my claim is that this matrix is telling us something about the so-called tangent space of a point on this variety. Okay, so pick some point here. There's some, if you zoom in a lot, this is gonna look like a linear space, okay? And that has a tangent space at some point P, Tp of x. So that's, I claim this is really telling us what that is. Okay. Oh, I should really actually, let's see. Tangent space is the translate that goes through the origin. And then if you want to kind of embed it in the same picture, then you just shift it up. Okay. Tangent space is vector space. Let's check. Somebody give me a point on the circle.
1, 0.
1, 0. That's my favorite one because I don't have to do anything. Thank you. All right. So what does this vector look like when I evaluate it? Dx f at x equals 1, 0. 1, 0. Sorry, 2, 0. Yeah. So at 1, 0, I'm getting the vector 2, 0. Okay.
Right.
But I want the kernel of it, right? Which is of course orthogonal to the row space. Okay, so kernel is yeah, 0, span of this. Okay, that's the vertical. Yeah. Yay, we now know how to take tangent spaces. Great. But there is this one thing that is kind of really annoying, and it's singular points on a variety. So we're gonna have to just a brief discussion of this, so you don't fall into pitfall. So there's no ambiguity of what the tangent space is here. The circle is a smooth manifold. Tangent space is well defined. There's several ways to define it. We're not going to really get into it, but there is a setting where it is ambiguous what you would want for the tangent space. And that is a variety that looks like this. Now, indeed, along any of the smooth points where when you zoom up, you just get a linear space, no problem. Like tangent space is the best local first order approximation of this. But here, you might have two candidates for what you might want to be the tangent space. One is just following the exact definition I gave you, in which case everything is the tangent space. And the other is maybe I kind of want like these two lines together to be like the tangent space. Okay. So the tangent cone. That's not the one we're going to deal with. We're going to deal with the tangent space as defined this way. But we're going to see that something kind of goes wrong at these places, and that's actually going to be our definition of being singular. So
Are these the points where the Jacobian fails to be invertible?
So before we had a 1/2 Jacobian.
That
You're not going to be
makes
invertible
sense.
because it's not square. We will have to invert some Jacobians. And thank goodness that we assumed in the homotopy that our system is square so that we can actually take the inverse. But we're not there yet. So right now, let me just write down two descriptions of this nodal cubic. So the first one, this is a v of y squared minus x squared times x plus 1. But it's also the image of t goes to t squared minus 1, t cubed minus t. You're about to see two conflicting ideas of tangency here. Okay. See the first one. So the Jacobian, the implicit system, is going to be yeah, okay, so what is this? This is like negative 3x squared minus 2x as the first part, and 2y's. At equals 0, 0. By the way, that's this point. This is 0, 0. Kernel is everything. That means we have 5 minutes left. And that's what I promised. Right? And of course, like if we pick a different point on here, so what do we gotta do? We gotta pick any x value, -1, comma 0, maybe? See this one? Here it's gonna work just fine. Right? We plug in -1, comma 0. We get something non-zero, -3 plus 2, -1. Yeah, we get this. Okay. So again, we're getting something orthogonal and space. Okay. This kernel is orthogonal to row space. Yeah. We remember our linear algebra. So that's fine. So that works really nicely. Right. But it's not going to work nicely there. And so that's going to be our definition of these. Point. Sorry. Evaluated. Sorry, let's say P has a dimension greater than. I'm totally cheating with this definition. Because this requires you to know what the dimension of a variety is. Okay. So that, look, we can look at a picture. You go, yeah, this is one dimensional, it's a curve. Fine, right? The problem with this definition slightly is the dimension of a variety is actually the generic dimension of the kernel, the Jacobian. So in other words, for almost all points on your variety, your the kernel of the Jacobian is going to have some dimension, but then at special places, that dimension is going to go beyond. Those ones are called singular. Okay, so this is also requiring some notion of generic and probability 1 that we haven't talked about yet. Okay. But if I tell you this is a variety, it's one-dimensional, tell me what the singular points are, you can write down the equations. You're asking for when the rank of this matrix goes down. Okay, so the dimension of the kernel goes up. Okay, we're done. So next time we'll start by actually getting tangent directions that you'd like, for example, like this one, from this map, because this map actually doesn't really see that singular point. Okay, and then we will continue with multivariate homotopy continuation. We will apply the good old-fashioned chain rule, this time in the multivariate setting to get a Davydenko differential equation. And then we will see that things at the end of these paths can be worse than before. And we'll handle those. Your definition of a Newton step and an Euler step is exactly the same. Replace derivative with Jacobian. Replace putting it in the denominator with taking the inverse. Okay. And homework 2 is up. The only coding part is that you have to code multivariate homotopy continuation, but you can work together. You can work together. You can work with me. You can share things on the Discord. Okay, so for the coding part, a bunch of functions which do what we're doing this week. And also you can model it all after the univariate setting that we've already coded, right? It's already implemented, all right? And then there's a couple of theory questions, which you should be equipped to solve now. And that's all. So, okay, so I'm gonna stop the recording now. Thank you.